I work on developing Tcl core. Sometimes I make releases. Wanted to talk about the Hash Array-Mapped Trie, or sometimes I hear it's trie. I don't know the definite on that. This is a new data structure, if you'll allow me to call something new that's between 15 and 20 years old. It's newer than Tcl. So, and my strategy here is to try to, if people know this data structure great, you can just take a nap for now, but anyone who's not accustomed to it, my strategy is to try to start you with something I believe you know, and take you step by step to get to this thing, and hopefully by the time we finish the journey, you'll have an understanding of it. Just very quickly, to set the stage, we're talking about hash maps. This is any time you're using a key to look up a value. We have it in Tcl in dictionaries and array variables. It also shows up in a lot of name lookups, so just the inherent operations of Tcl where I'm evaluating a command, I grab that first word and it's a string, I put it into a hash map in order to pull out the command procedure or the bytecode that I need to compile to. It's inherently in the operations of Tcl in many, many places, this operation of a hash map. And in existing Tcl, a lot of this is through the use of the Tcl hash table struct and associated set of routines. So just to get a very simplified picture of what is this hash mapping and how is it conceptually done, the idea is I want to enable the quick lookup of a key value pair by its key. And you do this by having a hash function on hand, which maps your space of keys to an index. You want it to be an efficient routine because you're going to be calling it a lot. And you want it to distribute your domain of keys. You want the range of this function to distribute very evenly over the indices so that you get a nice spread. Then conceptually, all you do is you've got this enormous array, and for some reason the terminology is that you call each element in this array a bucket. And if I want to find one of my key value pairs, I apply the hash function, I take that index I got out and use that into my array, and then I decide, is a key value pair there, or is a key value pair not there? It's a quick way to look up. So that's the concept of hashing and a hash table, so to speak. But this is just sort of a conceptual picture. This isn't a reality, and the key reason it's not a reality is this business here. I am talking here in terms of using 64-bit hashes. So if I wanted to actually have an array to hold every element of a 64-bit hash, we're talking 16 exabytes of storage here. So that's not the practical way you implement this, but that's the picture to give you an idea of how these things work. So then the question is, how do you take this generalized picture and turn it into something practical you can actually code? This, as a review, is Tcl's existing solution to that. Instead of taking our hash function and looking it up in a big array, I have an extra step where I apply a mask to that hash. So I go ahead and I compute. In Tcl's case, Tcl actually uses 32-bit hash values, but the concept is the same. And rather than using all 32 of those bits, Tcl just slaps a mask on there and cuts out however many. For small hash tables, it only uses 2 bits, actually. And it can grow and shrink as it needs to accommodate the amount of storage you're actually making use of. But just as an illustration, I have here a hash table with only 8 elements in it. And the idea is that I've taken this conceptual one back here, and the masking effectively folds this thing on top of itself. And then you have these key value pairs then landing in new buckets according to the mask. And you can see that one of the things that happened is a couple of them landed in the same bucket, and now they're a chain. And this is actually the strategy that Tcl's hash table makes use of, is to do the chaining. Now what I'm going to try to talk to, so that sort of gives you the ground level of what I think you know. Now I want to try that, go from what you know step by step to something, to the hand. Back to that 64 2 to the 64 array, let's not think of it an array anymore. Let's think of these buckets as being the leaves of a binary tree. So I've taken my problem of it being too darn big and I've tripled it. So this is not a good practical step, but it's a good conceptual step because it lets us start thinking about this data in a new way. And the idea here is that if I've got a hash, I'm going to use the bits of my hash as directions in following the path down this binary tree. I got a 0, I'll go to the left. I got a 1, I go to the right. Keep following until I run out of bits and I land in one of the buckets. And then once I'm in a bucket, did I find the key value that I was looking for, or did I not find it? So certainly as a functional description, you can see that this does the job. But the size is still a huge problem. So we start doing the obvious things of if we have a huge amount of space and almost none of it is actually storing anything. So let's get rid of all the stuff that's not storing anything. So now I still have all of these paths I can follow with the bits of my hash, and I can land into the key value pairs that are stored, but I'm not going to bother storing all of them that don't have anything in them. And any path that I come to that just comes to an end, I can know without following it all the way down that that was a dead-end path and there was nothing to find there. This is pretty simple and huge savings at that point. Then we can notice that a lot of the remaining structure of these paths to the leaves have chains like this, where I'm following the path, la-di-da-di-da, and there's no actual decision taking place here. Because of what the data is, I'm just taking lots and lots of steps to get to a predetermined location. So if we want to eliminate that, here's the catch on that. As things are in this picture, when I get to a key value pair, I've followed every bit of my hash to get there. So by the time I get there, I know what hash value got me there. If I don't want to take every step, I can collapse those chains, but I need, when I get to the end of my journey, for it to have stored the hash and tell me what the hash is. So that's what the next step is. I pull up all those long chains, don't need them, but the price I pay is at each one of these leaf locations, I'm now storing the hash value that the leaf would be if I had followed the paths all the way down. Okay, I'm seeing at least a few nods, so I don't think I've confused anything too terribly. So this is getting to be a much smaller picture. That seems like a good thing. Now the next thing I'm going to do is I have still, in this picture, this similar kind of chain here where I've got multiple steps being taken, but there's nothing happening here. There's no value. There's no decision guiding the search. So I want to get rid of that as well. And I run into the same issue that I want to get from here to here in one step instead of two, but I don't want to lose the knowledge I got from taking those steps. So the way I can achieve that is to store the information in each of these nodes of what their identity is in the complete tree. So even though I'm not storing the complete tree anymore, each piece still remembers where it was in the total structure. So that gets me to this, where I've eliminated that double step, and I've tacked on to every one of the nodes this identifier value of where it was in the complete picture. Let's see. Yeah. So now we get to the one that unfortunately is a little bit of a leap.
Can I ask a question right there?
Yeah.
Is that, so the ping thing, that's like, so you're sort of branching one way or the other based on bits in the hash, right?
Yeah.
So is the ping thing sort of telling you which bit you're branching on?
Yeah. So we're in the original binary tree. every level we go deeper, we add another bit to the path that's taken us there. So you can think of each one of these being identified by the prefix of the hash that got you to that point. And so in this pink, I'm storing that prefix.
Okay.
That's an identifier for where I am in the total structure, but I don't need the total structure if I've stored that identifier. So this next leap I'm going to make from this slide to the next, I'm going to stop drawing kind of a conceptual picture of the tree. I'm going to try to give a picture that gets at the implementation. So unfortunately, it's a little bit of a leap if you don't know how the parts go from one to the other. Notice that I've got 4 nodes here in this tree, and I'm going to have 4 nodes on the next slide as well. And there's a root with 2 children, and then one of those children has a child as well. So that is going to give us sort of a handle to grab hold of the next bit. So let's look at the root node here. I've got its identity, and it has 2 children. So what I'm going to do is on the next one, I've still got that root node, and I'm explicitly putting in that I'm storing pointers which point to those 2 children. So there's nothing really different there. It's just a more concrete depiction of the storage that's involved in getting that done. Now if I look at the left child, this is a node which has 2 children, but they're both leaves. And so what's going to happen there is I'm going to go ahead and pull those leaves up into the node. Rather than following a pointer to get to them, I'm going to go ahead and have those leaf values in the structure. And at the same time, I'm going to do a little shuffling around where instead of having the hash and the key value pointers paired up, I'm going to pull all the hashes to the beginning, and then I'm going to have all the key value pointers after them. So the idea is that I have in parallel, here are the hashes of my children, here are the key value pairs of my children.
Don?
Yeah.
I'm sorry, maybe I got lost. The 0011 for the root, I would have thought that would have been 0, all zeros. Are those numbers not?
The numbers to the side are the array map encoding, which I haven't told you about
Oh,
yet.
okay, thank you.
And then likewise here, this node had 1 child that was another node and 1 child that was a leaf. So I pull its leaf's hash up, I pull its leaf up, and then this is just a pointer to the child node. This one is very much just like this one. So this is just a way of pulling all that information into a structure. The depiction here, let's use the colors. The yellow is some control information, describes how things are operating. Pink is the identity of the node. The greens are the hashes of my children. The blues are the key value pointers of my children. And the whites are the child nodes. And the idea is that once you get past the pink, the rest of the structure is a general array. It's a pointer array. And in the struct that I have, it is literally just a field called slots. And the trick here is how to make use of this general set of slots in this particular way, knowing that some slots mean some things and some slots mean other things. And that encoding is what's in this yellow. And that encoding is what I've written the bits for here. So to explain the bits, the meaning of the bits, I've got a 4-bit encoding. The first 2 bits tell me about my key value children. And the last 2 bits tell me about my subnode children. So if I've got 2 zeros, that means I don't have any key value children. And 2 ones, it means my left child is a subnode and my right child is a subnode. So it's just a indicator bit kind of thing. Nothing more complicated than that. Likewise here, Both of my children are key value pairs. None of them are subnodes. So the only one that's interesting is this one here. I know that I've got one child which is a key value pair, and I've got one child which is a subnode, but which? Was it left or right? And that's encoded in these bits here. So this is telling me that the right child, sorry, these encodings are arbitrary, so you got to remember what the system is. The left child was the key value, and the right child was the subnode.
Is it always the case that the first 2 bits are the inverse of the second 2 bits?
Yes.
Okay.
Yes, that's a constraint. This is not as compactive an encoding as it could be. I'm using more bits than I have actual information, but it's simpler to decode. Okay, so that was kind of the big step. I was going from the last slide to this slide. Did I lose anybody terribly at that point? This is the HAMT. Now, I think I missed, as I was going by, defining some of the terminology. Once you've got a structure where it has a tree with all the information at the bottom and using an index path to lead you on a path through it, that's a tree in the sense of retrieval. This is an old data structure, been around for a long time. And if your index, which is driving you down, is a hash, you can call it a hash tree. Then, at this point where I'm doing this business with the slot array and having to decode it along the way, that's where that operation is known as an array map. So I'm using an array map to build my hash tree, Hash Array-Mapped Trie, HAMT. That's the data structure. So if you followed me and didn't get too lost, you now, and you didn't know about it already, now you know about it. Yes?
Could you repeat that definition of the array map you just stated?
I don't know that it was quite as highfalutin as a definition, but the idea is that I've got an array where I store information about my children, and I also have a map which tells me how to interpret the elements of the array properly. And in this case, the map is the 4-bit encoding. And this has written down what I described orally about how to decode those 4-bit codes. So now that we've got a data structure, let's try to do something with it so we can make sure we've got an understanding of how these things operate. This is back to the big picture of the hash tree, and for illustration, I've got 5 key values stored in this thing. Let's remove that one. Well, in the Tcl hash table, that corresponds to let's remove one of these. And simple operation, I want to remove it. Well, I find it and I remove it. And I've got a new hash map which doesn't have that key value pair in it. The key thing about this is this is a destructive operation. When I'm done, I don't have the one that I used to anymore. I've got a new one with the value removed, which is what I wanted. But if for some reason I wanted to have both hash maps still around, I don't have that with this operation. I would have to make a copy of the first one and then remove from the copy so that I would have both.
What's an example where you want to do that?
The dict command gives you a way to access dictionaries which are built on these hash tables. And because it presents Tcl values which aren't allowed to change, I have the whole copy on write dance I have to do. If I have a dictionary in variable A and in variable B, and I do operations on this one, I can't let A change value out from under me. So that would be a situation where I would want to make a copy before I make a modification. The contrast with the HAMT is that I can play a more elaborate game of how we do removal. So in the HAMT picture, what I'm trying to do is I'm trying to remove this guy here. And what I do is I don't go down the tree and remove him. What I do is I start building a new tree to represent the hash map that has that item removed. So conceptually, yeah, I want to remove this. And I would remove the child and I would remove the hash that goes with it. And when I did that, I would come up with a node that only had one child. And nodes that only have one child are forbidden in this structure. So I would have to lift that up, and then this in the parent would become a new key value child. So the result of all of that is I would have a new root node that looks like this. I've got its identity, I've got a hash that I copied from here, I've got the corresponding key value I copied from here, and I want the old child, I can just point to it. So now I've got a tree rooted at old, which is the old hash map, and I've got a tree rooted at new, which is the new hash map. This has the item removed. The old one does not have the item removed, and I've got both. And I haven't made a complete copy to do that. I've made a partial copy. And the key here is that this data structure presents something known as immutability. Once you've created one of these things, the idea is you never change it. You can, if you want to remove from it, what you actually do is you create a new one, which is the hash map with the removal applied. The concept here is you have your values are read-only structures, and this should be familiar to Tcl programming because this is the way Tcl values work. When you get a value, we say everything is a string, but a lot of the meaning of that is everything's a value. I can count on a thing being a thing being a thing, and it's not some identifier. Forget I said that. That goes down the wrong path. But the idea is that I don't need to copy and write these structures because they're inherently what they are, in contrast to the Tcl hash table where I have to do this copy and write business. Now's when I let one secret out of the bag. I made all my pretty pictures using binary trees because they're easy to draw and they're easy to see and understand. There was nothing essential in the way you did this, that it had to be binary. And my hash maps were 2 bits to tell me about my children. There's no practical way to use 2 bits. I'm going to use 64 bits. So my map is actually going to be 2 64-bit maps, guiding me on my 64 children at every node. And I've got a 64-array tree. And this data structure then becomes something on steroids, so to speak. With a tree that wide, it becomes very shallow. And even that conceptual 16 exabyte storage array can be completely reached, even in the fullest usage, imagining you had such storage available, in only 11 steps. This is what makes something like this somewhat practical. Is it logarithmic? Yeah, it's logarithmic, but it's tiny logarithmic. That combined with the essential the good match of the efficiency of the array map operations to things like cache lines, to things like CPUs being good at that sort of thing, makes these things practical, even though they have an appearance of being more complex. Let's look at how it measures up. So in order to play with this data structure, I created a Tcl command to operate it. I called the command the HAMT, and it has many subcommands in common with the dict. So then the dict is a way to manipulate the old Tcl hash table. The idea isn't to create a replacement for the dict. The idea is just to have 2 commands which can do operations in parallel and demonstrate the functioning of the underlying data structure. So if I create a list of 20,000 random numbers, and then I build a dict out of it, so I've got now 10,000 key value pairs in my dictionary, and I loop through the keys and one by one remove them from the structure until the thing's gone. And I do it in a stupid way. I get something that takes me 24 seconds to get done. 10,000 is not a huge number, so that's concerning. And seasoned Tcl programmers will know what the problem is that I'm operating on a value and then storing back into the same variable, and there's this whole sharing question. And I'm forcing myself into this copy on write. And this, what this is demonstrating is that this question of sharing and this question of copying is right there in the script programmer's face. They've got to be aware of this, and they've got to avoid coding that way. So how can you avoid coding that way? There's the K is one of the common things that's offered as a way out of this. For the dictionary, there's even a completely different subcommand, dict on set, that operates on a variable instead of on a value, that sidesteps. But the HAMT is that issue doesn't even come up. It can't happen. It's not in the realm of possibility of the structure the way it's designed. So I can code in the same way, parallel, and I get something that completes in 77 milliseconds. So that's a big win. But if I then apply my learning curve, my hard-fought battle scars of using dict, I know I should use dict on set. And dict on set is faster. So I'm not at the point where I can knock dict off the hill and claim total victory, but it's in the order of magnitude. And as a prototype, I find that encouraging. 5 minutes, okay, I better move along. Our enemy is making copies. So if you can avoid copy on write, you should, and if you can create structures that inherently avoid copy on write, so much the better when it comes to avoiding catastrophe. I'm going to skip past this. Quick summary. I wanted to have one example of where HAMT actually was better, and it's better at merging. HAMT tends to use more memory, for one. But if you're going to keep a collection, it's going to do all that sharing, it ought to use less. It all depends on how you're going to use this, how you're going to use the hash map. The key difference is this question of immutability and the kind of benefits that you can pull out of having a structure you can program with in different ways. So here are some of the ways that, at least in concept, I think this kind of a structure opens up. If I've got values which are never going to change, I worry a lot less about sharing them. I don't care how many people read this thing that never changes. I can't get in trouble because no one's going to write it. And so this sort of inherently opens up this notion of sharing, in particular sharing on threads is where I see big opportunity here. Because right now, if you want to do multi-threaded stuff, there's just a ton of copying involved in that. If I can keep every element of my history as I transform a hash map, I can keep the particular checkpoints that are valuable. And so in particular, when I go to create an interp, I fill a hash table with a built-in command set. It'd be handy if I could just remember that one. And the next time I create an interp, I just put it in, instead of having to fill the hash table again with this known set. Control teardowns. How many people have been through debugging namespace delete? Only me, because I'm me and a handful of others who actually make the core work. Because we've got that teardown where I'm going to loop through the hash table of commands in this namespace and call each of their destructors effectively. And those destructors can do things like remove other commands from the namespace. So the thing is changing out from under me. This loop has to be complicated. You can't even do a regular iteration. You have to keep asking for the first one again and again. And then you've got to protect yourself against endless loops. It's a complicated mess. But what if I were looping not through the changing thing, but looping through the fixed set of commands that was there at the beginning? And yeah, it can do other things and it can create a mess and it might not get the job fully done if it does strange things. But at least my iteration isn't complicated. And when the iteration is complete, then I can look again. And it enables that kind of simplification of programming. We have a lot of places where we do lookups and then we remember epochs to make sure that the lookups haven't gone stale. If we don't remember an epoch, but we just remember what map we pulled it from, and by remembering it, the map stays there, then what map am I looking from becomes effectively my epoch. And there's a question here of scaling. In the Tcl hash table, we got this long spine. And so at some point, that becomes difficult to allocate. And especially if you're using Tcl's allocator, which is limited. You're basically not going to go past the place where that craps out. Whereas the Hash Array-Mapped Trie, all the pieces are no more than a few hundred pointers in size. So as long as you don't run out of memory, you should be able to continue allocating pieces and not have the problem of allocating one big thing. If you want to take a look at this, I have a branched EGP refactor on the core Tcl repository. There also is a subcommand HAMT info, which will tell you statistical things about the structure. Feedback would be great. Let me just mention the relaxed radix balanced tree. So this talk has been about the HAMT, which is about hash maps. The HAMT is to the hash map as the RRB tree is to sequences. And this is the other big piece of Tcl, are sequences, lists and strings. And so if it turns out that there's useful benefits to using the HAMT for the hash map pieces, there may very well be benefits to using the RRB tree for the sequence pieces. It's worth an experiment at least, and that's where I'm pursuing, is trying these experiments, seeing where they pay off and where they don't. And I work in a research lab, so our conclusion always has to be we need to do further research. So we need to do further research, and that's enough for now. Thank you for your attention. Thanks for keeping me on time. Yes, sir.
Can you get does the implementation have a data structure as an extension so I can backport and do the existing Tcl test with it? Or is it built into
On that branch, I have done this code in 3 new files: tcl'-hampt.h, tcl'-hampt.c, and tcl'-hampt.obj.c. I have it in place to just be built into the core that builds on that branch, but I don't think I've used anything that would make it impossible to turn that into an extension. And that may very well be the fate of this work. I don't know. Yes, sir.
You said some new data structure. Are there any patent issues?
I don't know. I never looked to these things, and so I don't have a good answer for you. Since it's in use in so many places, I would suspect not, or I would suspect other people are running the same risk.
Just asking.
Yes, sir.
The Wikipedia page on HAMT doesn't indicate any patents rather than just the talk page.
Okay. That's a good sign.
It's a good sign.
John?
I was just thinking I've got a problem that this is directly applicable to. I'm trying to index 3D coordinates in space. And that's one of those things where a tree is going to be a heck of a lot more efficient because I have a function that can tell me greater than less than in 3D coordinates.
One of the things I found exciting about Kyan's talk is that he's sort of effectively demonstrating the cost of copies, and especially unneeded copies. And although he's taking a different approach to remedying that, I think that gives me a sense that there are gains to be made. If you can restructure things so few